And now we have the last part of our discussion on fluid motion. We look at a few examples. We have examples part 2. First, we have sample problem number 3. A garden hose is attached to a faucet at ground level. The other end of the hose is taken to the second floor of the house. The speed of the water as it comes out of the faucet is 2 meters per second. The faucet that is at ground level. What is the minimum water pressure at the faucet needed so that water comes out of the other end of the hose if the second floor is 5 meters above the ground? So we have two positions here. The position, one end of the garden hose at the faucet at ground level, and then the other end of the hose at the second floor of the house. So the first position is at the faucet at ground level. The speed of water at that position is 2 meters per second. So let V1 be equal to 2 meters per second. The faucet is at ground level. So let Y1 be equal to 0. What minimum pressure is needed so that water comes out of the other end of the hose? At the very minimum, the speed of water at the other end of the hose must be equal to 0, V2 minimum, such that water is simply dripping out of the hose at the mouth of the hose, but it's still coming out of the hose. So V2 minimum is equal to 0. What is the pressure at position 1, P1 minimum, such that water is still coming out of the other end of the hose? So that's what the problem is asking for. The second position, the height of the second position is given. The second floor is 5 meters above the ground, so let Y2 be equal to 5 meters. The fluid in question is water. We know the volume density of water to be 998 kilogram per cubic meter. The mouth of the hose on the second level is open. It's exposed to the atmosphere. So the pressure at position 2 is 1 atmosphere. 1.01 times 10 to the 5th power Pascal. So again, the problem does not mention the pressure at the second position at the other end of the hose. But since the other end of the hose is open to the atmosphere, automatically the pressure at the other end of the hose is atmospheric pressure. So P2 is equal to 1 atmosphere. Now, Bernoulli's equation tells us P1 plus 1 half rho V1 squared plus rho GY1 is equal to P2 plus 1 half rho V2 squared plus rho GY2. P1 minimum we are looking for. Rho, density of the fluid. The fluid is water. We know the density of water, rho water. So replace rho with rho water. V1, we know to be 2 meters. So let that just be V1 squared. Rho GY1, Y1 is 0. Therefore, rho GY1 is just 0. P2, we know to be 1 atmosphere. 1 half rho water V2 minimum. V2 is V2 minimum. So V2 minimum squared plus rho water GY2. We know Y2 5 meters. Now V2 minimum we have set to 0. So 1 half rho water V2 minimum squared is just 0. So we have P1 minimum plus 1 half rho water V1 squared is equal to P2 plus raw water GY2. Isolating P1 minimum and looking at the known values, we know all these variables kompleto. So plot in the variables, the values in the variables, and we are able to calculate P1 minimum. Thus, P1 minimum is equal to 147,906.000 Pascal or 1.479 times 10 to the 5th power pascals. Next, we have sample problem number 4. A horizontal pipe tapers from A1 equal to 1.2 times 10 to the negative 3 power meter squared to A2 is equal to 0.60 times 10 to the negative 3 meter squared. Water flows through the pipe. The pressure difference between the wide and narrow sections of the pipe is 4,120.0 pascals. Determine the volume flow rate of the water. A1 is given 1.2 times 10 to the negative 3 meters squared. The same goes for A2. 0.60 times 10 to the negative 3 meter squared. The pressure difference at these two areas, delta P, is given to be 4,120 pascals. Water is the fluid in question. Water is flowing through the pipe. We know the volume density of water to be 998 kilogram per cubic meter. The pipe is horizontal, therefore the centers of the two cross-section areas is at the same height. Since there's only one level or one height, let's set the height to 0. So y1 is equal to y2 is equal to 0. Determine the volume flow rate of the water. We are looking for RV, the volume flow rate of the fluid. And continuity equation tells us that the volume flow rate, RV, is constant and it's just equal to A times V. We have two locations, location 1 and location 2. So we have RV is equal to A1 V1 is equal to A2 V2. A1 V1 is equal to A2 V2. Isolating V2, we get V2 is equal to A1 V1 over A2. We don't know V1, so we can't calculate V2. We need V2 or V1 to be able to determine the volume flow rate. So we either need to get V1 or V2. V2 is equal to A1 V1 over A2. We can use this in combination with Bernoulli's equation. Bernoulli's equation, you have P1 plus 1 half rho V1 squared plus rho GY1 is equal to P2 plus 1 half rho V2 squared plus rho GY2. Same level, y1 is equal to y2 is equal to 0. Therefore, rho gy1 and rho gy2 both are equal to 0. And the volume density rho is just equal to raw water, 998 kilogram per cubic meter. The pressure difference is given by the problem. Pressure difference between A1 and A2 is just P1 and P2. P1 minus P2 is equal to delta P. The pressure difference between A1 and A2. If you transfer P2 to the other side, you have P1 minus P2. So transfer 1/2 raw water V1 squared to the other side so that we are able to isolate P1 minus P2. And that will give you 1/2 raw water times V2 squared minus V1 squared. V2 we know to be A1 V1 over A2. So V2 squared is A1 squared V1 squared over VA2 squared. Delta P therefore is equal to 1/2 raw water times A1 squared over A2 squared minus 1 times V1 squared. So we isolate V1. Okay, so we have V1 squared. Plotting in the values, we see that the only unknown is V1. So isolate V1 and we are able to calculate V1 to be 1.65896685 meters per second. Knowing V1, we are now able to calculate the volume flow rate. RV is equal to A1 V1. We know A1. We know V1, we are able to calculate RV to be 1.991 times 10 to the negative 3 cubic meters per second. And that's it for this video. That's it for our discussion on fluid motion. So thank you for watching.